Welcome back, and today in this video we're going to take a little bit of an introduction into methods of estimation. Chapter 9 here, and in Chapter 10, the next few videos, we're going to start getting into things like confidence intervals and using our statistics to infer what we think the population parameters are. All right, so in this section we're just going to look at a brief introduction into some terminology and notation for what we do with estimation in a general sense, right? So you can take a sample and compute a statistic, right? We'll get a value and we can use that to estimate the parameter. That's referred to as a point estimate, right? So some common examples of point estimates would be things like the sample mean, x bar, as a point estimate for the population mean. We can use the sample variance, s squared, as a point estimate for the population variance, and things like that. Now, whenever you have an estimator, we assume it's going to have some error, right? So what's going to make an estimator a good estimator, right? We know that there is statistics like x bar, which is the sample mean, but what about the sample median, right? Or what about the sample mode? Why not use the sample median to estimate the population mean? Or why not use the sample mode to estimate the population mean? Or all of those okay, right? Well, a good estimator should have a mean value that's equal to the parameter being estimated in a theoretical sense. The expected value of your point estimate should be equal to the parameter, okay? And I'll briefly introduce this or illustrate this here shortly, but let's write out our first definition here. A statistic, and this could be x bar, it could be s squared, it could be any statistic. This is theta hat, is said to be unbiased, to be an unbiased estimator. Unbiased estimator of the parameter theta if the expected value of theta hat of the point estimate is equal to the parameter. Okay, is equal to the parameter. So for example, think about x bar. X bar is equal to 1 over n times the sum as I goes from 1 to n of your observations xi. All right. Well, what is your expected value then of x bar? Well, this would be the expected value of 1 over n times the sum as I goes from 1 to n of xi. And with the linearity of the expected value, remember, these are just adding a bunch of terms up, right? So we can write this as 1 over n times the sum of the expected value of each of the xi's. And, well, what's the expected value of x? Well, if x comes from a population, and the population has some mean mu. So by definition, the expected value of a random variable x is mu by definition. So we have the sum from I equals 1 to n of mu. This means we have mu plus mu plus mu. We have that n times. 1 over n times n mu. And so the n's cancel, and we just get mu. So the expected value of x bar is equal to mu. That's the population mean. X bar is an unbiased estimator of the population mean. This also should provide some insight then if you've ever wondered why, when computing s squared, the sample variance, why we divide by n minus 1 in the original definition for the sample variance, like we do right here, the sample variance, why we divide by n minus 1, that is actually so when we take this expected value of all of this stuff, that is so that S squared is an unbiased estimator of the population variance. All right, that is why we end up dividing by n minus 1. That expected value is doable, although it's a little bit more complex than this. So I will forgo that because we are not going to be doing exercises on proving things are unbiased estimators, but it is just nice to be aware. If you ever wondered why do we divide by n minus 1 for the sample variance and not n, that is so that it is in fact an unbiased estimator. Okay, now it is possible to have multiple unbiased estimators. If two estimators, theta hat 1 we'll say, and theta hat 2 are both unbiased, of the same parameter theta, then is there a way to choose one that is better? Well, sure. I would choose the one that has the less variance, right? Want to choose the one whose sampling distribution has less variance. Has less variance. And I would say that's somewhat just common sense, right? If both of these have the same expected value, right, but you're using it to estimate a parameter, right, then why not choose the one that's going to be more closely surrounding the expected value, right? Less variance means you're going to have, it's a narrower distribution. It's spread is closer to the expected value in the general sense, so why not choose that? Okay, just some things to think about. All right, cool, good. All right, so unbiased estimators, specifically the ones we'll be working with will be the sample mean x bar, and we will be working with the sample variance to talk about some things like the population variance or standard deviation. All right. So what we do is when we get these samples here, like X bar, right? The natural inclination to say, well, if I just take one X bar, one sample, right? Sure, the expected value is the population mean, but it doesn't necessarily mean that specific sample is a good representation of the mean, right? So what you could do in some sense is think about getting repeated samples of X bar, right? Take a multitude of samples and compute a multitude of X bars. And what this is saying is if you took the expected value of all of those X bars, right, kind of like a limit as n goes to infinity, the average of the averages, the average of X bar, remember X bar is an average, the average of the averages would in fact be mu, all right? But we can use a little bit of theory to forego some of that work if we're willing to not get a specific value, but how about a reasonable range? A reasonable range. We can talk about an interval estimate. An interval estimate of a population parameter is an interval of the form we have a lower bound estimate for our point estimate and an upper bound estimate. Okay, so what are these numbers? The lower point estimate and the upper point estimate are determined in a very specific way. They are determined so that the probability that your parameter is between these lower and upper bounds is equal to 1 minus alpha. This is just some percentage where 0 is less than alpha is less than 1. Some percentage, right? So alpha is sort of selected as saying, if you think about alpha, say alpha is 5%, then 1 minus alpha would be 95%, right? Which would give you sort of a window that is accepting 95% of the values, right? We have a probability of 1 minus alpha of selecting a random sample that produces an interval containing theta, containing your point estimate theta. Okay. The interval, this is what is called a confidence interval. And we always, well, we don't always, but we tend to say, it's a 95% confidence interval, or it's a 99% confidence interval, right? So it's prefaced with the percentage of confidence. That is 100 times 1 minus alpha percent. Confidence interval. Confidence interval. Confidence interval. Oh. And back, there we go. Confidence interval. All right. The interval, confidence interval. The 1 minus alpha, we refer to as the confidence coefficient. Confidence coefficient. Confidence coefficient, or degree of confidence. Or degree of confidence.